In this video, we're going to look at how to build an adjacency matrix. You can build an adjacency matrix for any network. So here's an example of a network. We've got points, vertices A, B, C, D, and E with E in the center. An adjacency matrix shows which vertices are connected to which others. So in some cases, there might be multiple connections or multiple edges between vertices, between nodes. So the way we build an adjacency matrix, you guys are all pretty used to building matrices at this point, is we construct it with A, B, C, D, E. So each of the vertices down the bottom, so down the side, and then the same thing up the top. A, B, C, D, E. The numbers we put in are how many connections there are between those two vertices. So between A and A, there are none. There are no loops. So a loop, if it was 1 between A and A, if that was a 1, we would have a loop like this. There's not, so that's a 0. Between A and B, there's 1. So that's this one here. Between A and C, there are, as far as I can see, no direct edges. Between A and D, there's 1, so this one here. Between A and E, there is also 1, just here. Okay, so then we go through the next one. Between B and A, there is 1 connection. Now you notice we've already written that here, so it's actually a duplication. With any adjacency matrix that's undirected, so you can flow both ways, we're always going to have complete symmetry between the two diagonal edges of the adjacency matrix. You'll see what I mean in a moment. Okay, between B and B, there are none, so there's no loops. Again, if there was 1 connection, it would look like this, going straight from B to B. Some of this stuff. Between B and C, we've got 1 connection. Between B and D, there are none. Between B and E, there are 2 connections. This one and this one. All right, between C and A, no connections. Again, you're noticing that this 0 here is the same as this one here. We've already filled in that information. In fact, we always tend to duplicate things with a undirected network. So that's 0 and 0. Between C and B, we have 1 connection. Between C and C, there are no connections. Between C and D, there's 1. Between C and E, there are 3 connections. So we've got 3 edges going from C to E. Nearly done. D to A, there's 1. D to B, there are none. D to C, there's 1 connection. D to D, there are no loops. And D to E, there's 1. All right, last one. E to A, we've got 1 connection. E to B, there are 2. E to C, there are 3. B there. E to D, there is 1 connection, and E to E, there are none. So if I just draw this line of symmetry down the middle, you should notice it's always the same. It's a direct reflection between the 2 sides. So this triangle of numbers and that triangle of numbers are exactly the same. Like I said, but that's because we're actually going both ways. In a moment when we get to directed networks, when an arrow only flows one way, it won't be the case. They won't be symmetrical. Okay, so that's how you draw an adjacency matrix. I'm going to have a look at a few features in the adjacency matrix now. So I'm going to look at features, and here's our examples. So firstly, if we have an isolated vertex, so it's actually not connected to the network at all, this is vertex A, and it's not connected to any of the other vertices. So that's why there's zeros all through that row, because A is completely disconnected. When we've got a loop, like I mentioned before, we actually have, so these are the diagonal numbers. Normally, they're all 0. If there's a 1 in these diagonal numbers, because that's F here and here, the diagonals are the connections to themselves, we have a 1 because there's actually a loop around F. So those are some of the key features of a network. If you've got 2s, it means that there are 2 connections between a couple of vertices. And again, you notice there's this reflection pattern going on where the numbers are the same the whole way across. So that again means that there's not a directed network. Okay, last section of this video. We'll have a look at directed networks. So in this network, we have vertex K, vertex A, and vertex B. Now, K is connected to A twice. And here, in the rows, we use this as coming from, and the columns where we're going to. So from K to A, there are 2 connections. From K to B, there are 3 connections. These 3 just here. From A to K, there are none. You can't go that way because there's an arrow saying it's a one-way direction. From A to A, there are no loops in there, so that's 0. From A to B, we have a one-way connection. Now from B, we can't go anywhere. B is pretty useless. We can't go to A. Nope. We can't go to K. So we've got some other terminology here. If we've got a vertex like K, where all of the edges are moving away, we call this a source. If we've got a vertex like B, where every edge is heading towards it, there are no edges leaving B, we call it a sink. So, reasonably easy to remember, a source is where something comes from, and a sink, well, you only put things down the sink. You don't take things out again, hopefully. And there you have an adjacency matrix. Now here, just labouring the point, if I do a line down the diagonal, they're no longer symmetrical because we've got these directional factors. With a undirected network, it doesn't really matter whether you say from or to on the rows or columns because it's going to be exactly the same if you flip it around. With a directed network, make sure that your rows are the from and your columns are the to. Okay, that's all done.